We're looking again at the mid-segment theorem here. In the kaleidoscope image, we know AE and BE are congruent, and AD and CD are congruent, and we want to show that CB is parallel to DE. So basically, we want to show that we have mid-segment, because then we know that CB would be parallel to DE, and also that DE would be half of what CB is. So let's take a closer look at the picture there. I'm going to zoom in real quick. And let's just look at all of that. Okay. So we know that AE and BE are congruent. That makes E the midpoint. We know that AD and CD are congruent. That makes D a midpoint. Therefore, DF, or DE rather, is a midsegment. If DE is the midsegment, then we know that CB is going to be parallel to DE. Okay? And that's basically it. That's what the midsegment theorem tells us. If these two are midpoints, then we know that DE is a midsegment, it's parallel, and it also is half, DE is half the length of CB. So again, we know that E is the midpoint of AB, D is the midpoint of AC, so DE is a midsegment, and therefore by the midsegment theorem, those two lines are parallel. Looking again at this picture, remember, whoops, let's zoom out real quick. We already stated in this picture that AD and CD were congruent. We also stated that AE and FB were congruent. And they're saying if we know that F is the midpoint of CB, then we know that CF is congruent to FB. And for example, we could say that FD is a midsegment, and that FD is equal to 1/2 of AB. So those would be things that we could say. And again, DF is the midsegment of triangle ABC. We'd know DF is parallel to AB, and we'd know that DF is half of AB. We would also know, since E is the midpoint, we could also say that EF is a midsegment of the triangle, and that EF is parallel to AC, and we could also say that EF is half of AC. So those are all things that we could say. Alright, now we're going to talk briefly about coordinate geometry, and it has to do with proving certain properties that are true in general rather than specific situations. So rather than using numbers to represent lengths, we use variables. And we want to always place the different figures that we're dealing with so that hopefully one vertex is at 0, 0. So if we were to do this, again, we would want horizontal and vertical segments on the axes, and we want one vertex at the origin and one or more sides on either the x-axis or the y-axis. So for the rectangle, it would look something like this, and what we'd do is we'd put here's 0, 0 for the x and y axes. We would say this length is h, so therefore, since this length is h, we would call this h0. We would call this length k, and these letters are chose arbitrarily. You can choose any letters you want, but let's call this length k. Therefore, this point right here would be 0k, and this point right here would be hk, because we would go to the right h and up k. Similarly, if we had a scalene triangle, we would have to use 3 different variables. So we would put one corner at 0, 0. We would make this length right here d, so this would be d0. And again, we'd have to say, and let me show you this real quick, the distance from here to here would be f, and the distance from here to here would be g. And again, those letters are chosen kind of arbitrarily. You could have chosen A, B, and C. Anything would have worked. But we'll use these to prove certain properties of different geometric figures. And what we do is use these letters so that we can show that it's true all of the time, rather than just with certain numbers. Okay? Alright, so it says, is there any way of using the side lengths in part B of example 3 without using the distance formula? So if we go back to example 3, example 3. For the rectangle, let's go back to it one more time. So part B of example 3, would we be able to find any distances without using the distance formula? Well, this length we would have to use the distance formula. For this length we would have to use the distance formula. But for this bottom one, we would be able to just use the distance from 0, 0 to D0, which would be D. Similar to the way that from 0, 0 to H0, the distance is H. So again, the distance would be D because it's horizontal. Horizontal and vertical distances, again, we don't need to use the distance formula. And we have a square with vertices at 0, 0, M0, and 0M, and we want to find the fourth vertex. This is what it's going to look like if we were to graph it. We would have our y-axis and our x-axis, and again, the distance M is going to be kind of arbitrary, so we'll call this M right here. So this would be M0 because it's on the x-axis. We want to go the same distance here as we do here. Hopefully that's about right. This point would be 0M because the distance would be M on the y-axis, and then it would look like this. Of course, this corner down here would be 0, 0. And the fourth axis, which is what they're asking for, this one up here, if we do that, the distance from here to here is M, so my x-coordinate is M. And going up, my y-coordinate is M as well. So the fourth vertex would be M, comma M. There we go. And that's it. Thank you.